By Thomas Kitching, UCL. There was much excitement when scientists witnessed the violent collision of two ultra-dense, massive stars more than 100 meters light-years from the Earth earlier this year. Not only did they catch the resulting gravitational waves, ripples in the fabric of space-time, they also saw a practically instantaneous flash of light. This is exciting in itself and was the first direct evidence for a merger of neutron stars. But from a cosmologist's perspective, the photo finish of the gravitational waves and the flash of light has at a stroke demolished years of research into a completely unrelated problem: why is the expansion of the universe accelerating? It turns out that space and time are actually mutable, pliable, flexible and wiggly, rather than constant, fixed or immovable. This has been known since Einstein published his theory of general relativity, which explains how gravity warps space-time. The subtle effects that this mutability causes need to be accounted for even in the GPS that makes your sat-nav and iPhone work. One prediction of Einstein's theory was that it should be possible for space-time to have waves in it, like the surface of the sea. These would be visible if one could, for example, smash together two black holes. This prediction was dramatically seen in the first detection of gravitational waves by the LIGO experiment in 2015. The discovery opened up a whole new way to probe the cosmos, and was awarded the Nobel Prize for Physics. Galaxy Cluster SDSS, what's pushing it apart at an accelerated rate? ESA, NASA, K. Sharon Tel Aviv University and EOF at Caltech. The new detection of gravitational waves from the merger of neutron stars also has profound implications for our understanding of the universe. However, for the cosmologists it was the flash of light 1.7 seconds after the gravitational waves that was the more intriguing observation. The cosmic speed camera 1.7 second time delay is important because it means that the gravitational waves and the light waves had been traveling at almost exactly the same speed. In fact, these are two of the most closely matched observed speeds ever. The two only differed by 1 part in 10 meters billion. To put this into context, if the speed cameras on the road could measure speed differences this finely, you would get a ticket for going 30.0000000000001 miles per hour in a 30 miles per hour zone. Compared to the best measurements cosmologists were hoping for in the future, this is a factor of 1,000,000 billion times better. Factoring in that the electromagnetic waves may have taken a bit of time to escape from the turmoil of a neutron-star collision, for all intents and purposes the speed difference is zero. Cosmology is in a bit of a pickle. We have a great model that can explain the evolution of the universe from a fraction of a second after the Big Bang, until now approximately 14 billion years later. The problem is that in order to explain all the observations, a mysterious energy called dark energy must be added to the models. Dark energy is a huge problem. It accounts for about 70% of all the energy in the universe, and we have absolutely no idea what it is. Dark energy is like an anti-gravitational effect that is pushing the universe apart and causing its expansion to accelerate. So to explain dark energy, cosmologists have attempted to change or replace Einstein's theory to see if a new theory of space-time could finally explain the effects of dark energy. One way that cosmologists tried to do this was by changing the speed in which gravitational waves and light traveled. There were many different theories that had this component, each with a peculiar name like quartic and quintic Galileons, vector tensor theories, generalized Proctor theories, B-gravity theories and so forth. Without data, any of the theories could have been correct, and there were many people hopeful that they could be the next Einstein and Newton. Where are we now? But now, in a single observation from a single neutron star merger, a wide variety of these have now been consigned to cosmological dustbin in a flurry of papers here, here and here. So no new Einstein yet. In the absence of compelling data, it is still possible that we can update Einstein so we can account for dark energy. But the wiggles from the gravitational wave data has left very little wriggle room. Artist's impression of the finished square kilometer array. Swinburne Astronomy Productions for SCAR Project Development Office, CC by SAR. The theories that have survived the pruning are much simpler than those that were allowed before, and the simplest theory, and the frontrunner, is that dark energy is the energy of empty space, and just happens to have the value we observe. Another explanation that has survived is that it's a Higgs-like field. The now famous Higgs boson is a manifestation of a Higgs field, the first scalar field observed in nature. This is a field that has a value at every point in spacetime, but no direction. analogy would be a pressure map on a weather forecast, values everywhere but no direction. A wind map, on the other hand, isn't a scalar field as it has speed and overall direction. Apart from Higgs, all particles in nature are associated with quantum fields that aren't scalar. But like the Higgs, dark energy could be an exception, a ubiquitous scalar field pushing the universe apart in every direction. Thank you. We won't have to wait long before new telescopes will test the remaining theories and a big piece of the cosmological puzzle will be completed. Thomas Kitching, reader in Astrophysics, UCL. This article was originally published on The Conversation. Read the original article.